Hello, we are Group 4 and I will be presenting about advanced manufacturing methods for wind turbine blades. Modern wind turbines are used worldwide for sustainable power. By 2040, 45% of global electricity generation is expected to be derived from renewable sources including wind. Thus, turbines are a fast-growing technology of both scientific and economic interest. Most commercial turbines are mounted on a horizontal axis with 3 blades. The electrical generation capacity ranges from 1 to 2.5 megawatts per turbine. The major mechanical components include the rotor blades, generator, and gearbox. The blades are mounted to a central shaft, which is connected to the gearbox and generator to convert the low-speed mechanical rotation into electricity. Power output is a function of the wind speed, air density, and blade radius. Since wind speed and air density depend on the location, the blade radius becomes the most important factor that can be maximized on a design basis. This means building larger and larger turbines, which creates a unique set of manufacturing challenges. There are 3 main steps to the current workflow for manufacturing turbine blades: material selection, the process itself, and finishing techniques. The blade materials must be selected for high stiffness, fatigue resistance, and low weight. Similar to the aircraft industry, aluminum, steel, and composites are typically used. The composite structures usually include filler fibers such as glass, aramid, or carbon fiber surrounded by a polymer matrix. The main process for blade manufacturing is vacuum-assisted resin transfer molding, which is done almost entirely by hand. Sheets of material are laid up into a female mold, which is then impregnated with a resin and cured under vacuum. Finally, a variety of coatings may be used to improve the exterior finish and provide surface protection. This protects the overall turbine efficiency from blade deterioration or environmental factors such as ice buildup. The construction of a typical blade consists of a hollow shell with 2 separately molded and bonded halves. The shell has a sandwich structure with outer layers of hard fibers and internal layers of soft support. Structural components such as spars and webs are then inserted into the shell after molding. Blades typically account for 1/5 of the cost of manufacturing onshore wind turbines, yet there are still an estimated 3,800 blade failures annually, which is a failure rate of 1.3%. That doesn't include deterioration and wear from environmental exposure, which result in reduced turbine efficiency. Turbine blades are subject to a range of aerodynamic, gravitational, and inertial forces. This loading can cause various failure mechanisms, which are exacerbated by issues resulting from manufacturing. Delamination can occur when air is trapped between the fiber bundles of a blade due to poor resin infusion. This causes cracking between the layers. Debonding is a deterioration of the adhesive agents that are used at the interface between various structural elements. When the adhesive has deteriorated enough, then the layers will separate. Finally, buckling occurs with overloading of the blade, where the shape changes and cracks. This may happen at lower loads than expected due to the compounding effects of other defects. Existing manufacturing methods for turbine blades are labor and cost intensive and can lead to manufacturing defects and variability. Therefore, our engineering problem of focus is: how can novel advanced manufacturing methods be applied in a cost-effective manner to improve reliability? In this context, reliability refers to consistent and intended performance achieved by a range of improvements such as durability, lifespan, and manufacturing quality. We conducted an extensive literature survey to improve each aspect of the manufacturing workflow: material, process, and post-process. 3 promising methods were identified: hybrid 3D printing, thermoplastic composites, and polyurethane coatings. Big Area Additive Manufacturing, or BAM, is an industrial variation of 3D printing. BAM uses screw injection molding of thermoplastic polymer pellets for precise control of melting and flow rates. Conventional subtractive manufacturing processes can also be applied after printing. Since traditionally machined parts require the removal of up to 90% of material, the use of BAM can reduce labor, material costs, and manufacturing time. A commercially available BAM unit can extrude 10 times as fast as a traditional 3D printer. Fiber-reinforced composites up to 6 meters in length can be directly printed. One limitation of BAM is part weakness in the Z direction due to sequential layer cooling. This constraint can be addressed by rotating the printed part to ensure that design loads are perpendicular to the Z direction. The use of hybrid 3D printing for turbine blade molds allows the blade to be molded in fewer sections. In addition to the aforementioned cost and time savings, this process will reduce human error and structural weak points. Most blades are manufactured from thermoset composites, which have specialized curing requirements and cannot be easily recycled or repaired. Thermoplastics therefore offer several advantages. Since they soften when heated and reform upon cooling, thermoplastics allow for the use of fusion welding and adhesives. Defects can be directly repaired during the manufacturing process. Additionally, curing ovens are no longer needed, reducing production energy usage by 95%. One limitation of thermoplastics is that they are not easily flowable, which makes them difficult to use in traditional infusion processes. Low viscosity monomer melts are being researched which can be injected and polymerized in situ. This method does require higher mold temperatures, for which heating would be an additional cost. As part of the turbine blade manufacturing workflow, thermoplastics offer processing cost improvements while maintaining the required mechanical properties. The infusion and curing time is reduced by 6 times, and the material is 20% less expensive than a traditional epoxy. Typically, the outer surfaces of turbine blades are coated with gel coats or paint to improve environmental resistance. Grip blasting can be used to increase the surface tension and roughness before coating. This helps the subsequent coating better adhere to the surface, improving durability and longevity. This diagram breaks down a simple step of aluminum oxide grit blasting in a dry nitrogen environment. The exterior surface of the resin, shown in red, is removed without damaging the reinforcement fibers. For the coating layer itself, thermosets are popular because their cross-linking adds improved wear resistance. However, they require high curing times and cannot be repaired. As an alternative, thermoplastic polyurethane is also highly fatigue and impact resistant. Polyurethane also cures more quickly than epoxy and has a low exothermic energy release, which makes it ideal for bonding to the blade material. Research has shown that silicon carbide reinforced thermoplastic polyurethane can increase fracture toughness by 48%, which is double of a traditional coating. Additional work has incorporated nanoscale fillers for further improvements in wear resistance and dissipating impact energy. For our design proposal, we combine these 3 advanced technologies. First, hybrid 3D printing will reduce failure points by creating larger and more uniform molds. For a single 30-meter blade mold, we expect a 35% shorter manufacturing time and 20% lower tooling cost. Secondly, thermoplastics will improve the molding procedure without sacrificing mechanical properties. The process is simplified, 6 times faster and 20 times less expensive than traditional epoxy. Finally, surface preparation and polyurethane coatings will further improve the wear and environmental resistance of the blade surface. The 3 technologies we described are well established in the lab scale and other industries. However, further work is needed to apply to turbine blade manufacturing at a repeatable and industrial scale. Expected development steps would include understanding the effects of various 3D printing parameters, investigating next-generation wide-high additive manufacturing to create even larger molds, analysis and testing to characterize the mechanical behavior of thermoplastic blades at industrial scale, and optimization of surface preparation and coating technologies. In conclusion, we've developed a novel process for wind turbine blades that integrates 3 advanced manufacturing methods. Combining hybrid 3D printing, thermoplastic composites, and polyurethane coatings allows for a wide variety of process improvements that will drastically improve reliability of turbine blades. Thanks for listening and take care.